Okay, so the way I'm going to do this is share my screen and my notebook. And so when I do that, I won't see the list of participants. Screen. Okay, here we go. So last time we talked about limits and colimits. Yes?
Can you let Melike in? I think she's in the waiting room.
Okay. Thank you. Let me see. Okay, good. Thank you. Okay, so last time we talked about limits and colimits, and there's a lot more that we could say, and we'll say some of it in seminars, but we need to keep moving. So we'll begin talking about adjoints, and at the end of the lecture today, we'll explain how adjoints are related to limits and colimits. So let me start with an example of a pair of functors which are related, whose composites are related by natural transformations. So fix a set X, and from a set we can define two functors from set to set. One of them is just product with that set. And the other is maps out of that set. So there's a set of maps from X to any other set. And I can consider the composite of these two functors in the two different orders. So I could first, so let's consider composites. So I could first cross with X and then apply Hom. So if I had a set Y and I crossed with X, and then I Hommed in from X, I would get the set of maps from X to Y cross X. And given a point of Y, there's a particular map of that form. So this is I'm going to call it co-Y. It's a kind of co-evaluation. It takes a point of the set Y to the map, which sends a point of X to the point of the product, which is Y comma X. And it's easy to check that this is natural in Y. So you can check this is a natural transformation. From the identity on set to the functor, which is Hom from X into blank cross X. So in that blank, I can put any other set. And I'll call it co for co-evaluation. And in the other direction, I could first Hom from X into some set and then cross with X. And given a pair of a map from X to Y and an element of X, I can evaluate the map on X and get an element of Y. So this sends a pair, a map F and a point of X little x to f of x. And this is called, I'll call it ev for evaluation. Okay, and this is also natural. So it's a natural transformation from hom x blank cross x to the identity functor. So I give you formulas for what these natural transformations are, and so to check that they're natural, you just compute. So pick a map from y to y prime and make sure the appropriate square commutes. And how are these two natural transformations related to each other? So I could compose again. In the first one, what did I do? The first one's here. So I first crossed with x, and then I hommed from x. And then I could cross with x again. Okay, so the two, these are related. Co and ev are related as follows. So if I do, I take co and I cross it with x, co cross the identity on x, I'll get a map into hom x, y cross x. And then there, what can I do? I can evaluate. I can evaluate on what? So this was co on y. And here I can evaluate on y cross x. And that will give me a point in y cross x. And if we follow this through, I have y, little y cross little x. Where does it go? Well, the co-evaluation goes to the map which sends x prime to y comma x prime. That's a map. And then the point x just goes to x. And now I need to evaluate this map, which sends x prime to y comma x prime. I need to evaluate that on x. So all I do is replace x prime with x. So that goes to y cross x. So this composite, which is evaluation of y cross x, precomposed with the co-evaluation cross the identity on x. This is just the identity on y cross x.
I'm sorry,
And
can you let in some people where you try to?
sure. Yeah,
Yeah,
thank you. Yeah, thank you. Let's see. There they are. Okay, looks like everybody's in now. Okay, and similarly, I could do it in the other direction. So I could take this evaluation and I could hom from x into the evaluation. So I could apply hom x blank to evaluation. And then what do I get? Let's see. So on the right-hand side, I would get hom x into y. And that would receive a map from hom x into hom xy cross X. Make room for everything. And then coming into that, I could consider the co-evaluation coming from Hom y to X. This would be co on the Hom. And this over here would be the Hom applied to the valuation on y. And let's compute the composite. So if I have a map, sorry, this was X into Y, not Y into X. So if I have a map from Y to X, what does the co-evaluation do? It's supposed to take little x to f, the pair, f comma x. And then what does the second map do? It composes with the evaluation. So this will map to, for every x, it just evaluates.
Excuse me,
gives the
Chris,
map.
could you answer a question?
Yes.
You say about an evaluation here, but could you remind what it is?
Yes. What's the question?
What is an evaluation here? What do you put in what?
In this last line?
Yeah.
Or in general. So in the last line, for every little x, we evaluate f on little x, so we compute f of x. And we do that for every little x, so it gives a map from big X to y. And what is that function? It's exactly f itself. That's what f does. F takes little x to f of x.
It means that this is this is a composition that is equal to the identity.
Yes. So that's exactly what we want to conclude. This composite, which is Hom x, which is a functor applied to the natural transformation yev, precomposed with the co-evaluation on Hom x. This is the identity. And so in both orders, when I compose in this way, I get the identity. And this example generalizes in the following way. So the definition is as follows, then we'll give lots of examples. We've actually already seen lots of examples implicitly. So in adjunction, this is what we're defining. Between categories C and D is the data of a pair of functors so there's a functor f from C to D, and there's a functor g from D to C. So f is going to be on the left, g on the right. So one is called left adjoint, the other right adjoint. And so it's a pair of functors back and forth and natural transformations. So this one is called left adjoint. This one's called right adjoint. The natural transformations will also have names. So they generalize evaluation and co-evaluation. So natural transformations, let's write those out. So there'll be a natural transformation from G followed by F. So G goes from D to C, F goes from C to D. So the whole thing goes from D to itself. That's not necessarily the identity, but it's comparable to the identity functor on D via natural transformation, which is called traditionally epsilon. So this is called co-unit. So this is what generalizes co-evaluation from the previous example. And in the other direction, I could consider first F, then G. So first left adjoint, then right adjoint. And this is the unit or evaluation, if you like. Sorry, it looks like it's the other way around. Co-unit is the evaluation and unit is the co-evaluation from this example above. Okay, so the way I remember which way they go is that here, when you read it off from left to right, the left functor, the left adjoint functor appears on the left, and here, the one in which the right adjoint functor is written second appears on the right. Okay, such that, so this is the data, and then it should satisfy some conditions. So we need these triple composites. And there are two ways to get a triple composite. You could compare, you could look at this triple composite, FGF, or the triple composite GFG. And let's see, doesn't matter which order I do them in, I think. So in the first one, I could look at the unit and apply F to it. So that would give a map, a natural transformation F eta from F to this triple composite. Or I could read the triple composite as having arisen from what? Precomposing the co-unit on F. So I could have applied the co-unit to F, and that would get me to F as well. So this here should be the identity. And similarly, if I do a similar thing here with the triple composite, I can apply G to the co-unit, or I could apply the unit to G. So these composites should be identities. And we verified this in our example above. So let me give a few more examples to see what this means. And the first example I'll give is, it's very similar, but it's kind of linearized version. But it's a very important example, especially in homological algebra. So suppose R and S are rings. So all my rings are always assumed to be unital. We can look at R and S modules, the categories of R and S modules.
May I ask another question?
Yes.
You say about unit, is it in a abelian category or something like that? I mean that there it can be that there is no unit in the category, as far as I understand. Is it a categorical unit here?
Is what a categorical unit? The unit in the ring?
No. You said a bit above about the unit, you define the unit, but I have, looks like I have missed the definition.
Of a unital ring?
No, not of a unital ring. Could you swipe a bit up?
Here?
Yeah, yeah, it C.
This unit.
Yeah.
This unit is a natural transformation. By definition, a unit for an adjunction is a natural transformation of this form such that it satisfies these identities.
Ah, you mean that this is a unit and co-unit for
Of an
natural
adjunction. So an adjunction between C and D it's a pair of functors, F and G back and forth,
I see.
together with two natural transformations called co-unit and unit that satisfy these identities. When you compose things in this way, you get the identities.
Thank you so much.
Okay, so let me give another example. It's very similar to the evaluation co-evaluation from before. With sets, it's a kind of linearized version of this. So suppose R and S are rings, and P is, let's see, an SR bimodule. We already gave an example, a pair of functors you get from an SR bimodule before. So we can tensor with that bimodule. That gives a functor from left R modules to left S modules. And we can also hum out of over S, hum out of P. And that produced an R module. So I think we did this even on the very first day. So that's a pair of functors that you can build from a bimodule, and they are adjoint to each other. So let's give the adjunction data. We have to give the unit and co-unit. So let me give first the unit. And I'll just tell you what its value is on a module. It'll be kind of, the naturality will be pretty obvious. So given, so what am I going to do? I'm going to apply first the right adjoint, which is the hum. So given an S module N, I will have hum. Right. Hum. Okay. Then I can tensor that over R with P. And I'll just tell you, this is going to be like this. Maybe I'll put it on the next line. So what does this do? I'm just going to give it to you on simple tensors, and you have to check that it satisfies the appropriate bilinearity. So given an element of P little x and a homomorphism from P to N, I just compute f of x. And you can check that that is bilinear over R with respect to the R action on the hum, so that that's a well-defined homomorphism out of the tensor product. You can also check that it's natural in N. And the co-unit, so I have to do it in the opposite direction. So given an R module, I first tensor it with P, and then I hum from P, and there should be a natural map sorry, I'm always confusing unit and co-unit. My apologies, just a sec. So what is this? This is co-unit. and this is unit. So this will send an element M of the module M to, has to be some homomorphism from P to P. What could it possibly be? It must be X tensor little m. And again, you can check that this is R linear. And we'll define a natural in M, and then using these formulas in a way very similar to how we check these identities for evaluation and co-evaluation for sets, you can see that this data forms an adjunction. It's a pair of functors back and forth with these natural transformations satisfying the correct identities. Okay, so this is, for us, in homological algebra, probably the most important example of an adjunction. Are there any questions about this? No? Okay, so let me give another typical example. So another typical example is a free forgetful adjunction. So let me do this for groups, and abelian groups. But it appears all over the place. So there's a functor free from set to group. So a set X goes to f of X. This is the free group on X. And given a group, I can forget that it's a group. I can forget the multiplication and the unit and how to take inverses. And so this will just be a group, say gamma, goes to the underlying set, gamma, as a set. So this is called free. And this is called forget, because you forget that you have a group structure and just remember that you have a set. And the claim is that these form an adjoint pair. So I have to give you unit and co-unit. So the first thing I could do, let's do this. Let's do G of gamma and then F. So this is going to be the co-unit.
And I have a question. How I see that if there is a free group, then we have a map to the set that just gets a group to its generators, right?
No.
Not its generators, just its elements.
But
A group doesn't have a preferred set of generators.
and if it's, for example, a Lie group, then would it map to an infinite non-countable set?
Yeah.
Okay. But looks like if you take a Lie group, for example, and get it to the set and then take a free group, then we wouldn't get the Lie group again, isn't it? Uh, do anyone hear me? I don't hear anything.
Yes,
Yeah,
I can hear you.
Probably. Oh, Christopher has disappeared.
He's already out. He should come back.
Hi, how long was I disconnected?
Since the last question, probably.
The last question, let's see. Screen. So I'm recording on one device and writing on another. Let me show you what I wrote and you tell me where I got cut off. So I was explaining two ways to talk about adjunctions. One was in terms of FG, eta, and epsilon, and the other was in terms of an isomorphism of Hom sets. Did you hear that?
We last wrote counit FG gamma to gamma.
Gamma. Up here.
Yes, counit.
Oh, goodness. Okay. So I said that you could work out the similar version for abelian groups. It's very similar. You just replace multiplication with addition. So I'll let you think about that. I'll also post the notes. But I should say again this part. So there's an alternative way to think of adjunctions. So the dilemma is that the datum of the adjunction involving FG, eta, and epsilon between two categories C and D, it's equivalent to another kind of datum, which is isomorphism of Hom sets between, so I can take an object X of little c, I can apply F to it, I get an object of D, and then I can Hom that into an object of D, Y. So I have a Hom set D inside D from Fx to Y. And that turns out to be isomorphic to homomorphism maps in C from X to GY. And this set of isomorphisms is natural in X and Y in a kind of obvious sense. So what I wanted to explain is how to construct this correspondence. The claim is, given a junction datum FG, eta, and epsilon, I get a sequence. I get a bunch of such isomorphisms which are natural in X and Y, and also conversely. So the correspondence goes as follows. Given the adjunction data FG, eta, epsilon.
Excuse me.
Yes.
As I remember, you didn't finish the example about free groups.
Yes, and
you were
I'm not.
about to use counit and.
Okay, but I'm gonna let you look at the notes later because we probably lost about 20 minutes.
Okay.
Mm-hmm. Okay, so the correspondence is as follows. Given a map in D from Fx to Y, I call it little phi. So that's right here. I can apply to that G, and then I'll get a map from GFX to GY, call it G phi. And then I can precompose that with the unit evaluated on X, which I already have, and the total composite will be a map from X to GY. So that gives a map from the set of maps from Fx to Y to the set of maps from X to GY. And the inverse map I claim is given as follows. So given a map from X to GY, call it C. I apply F to it. So I'll get a map from Fx to FGY. And then I can post-compose that with my co-unit. Altogether, that will give a map from Fx to Y. And I claim these two are inverse to each other. The reason they're inverse to each other is exactly because of these identities, that these two composites are the identity. Okay, so that's how you go from this kind of adjunction data, FG, eta, epsilon, to a bunch of natural isomorphisms between Hom sets of this form. And in the other direction, if I have a bunch of these isomorphisms of Hom sets, which are natural in X and Y of this form with F on the left and G on the right, then I need to produce for you eta and epsilon. And the way this works is as follows. So I let y, so I'm given these isomorphisms, I let y equal fx. And so the isomorphisms will in particular give me a correspondence between maps from fx to fx to maps from x to gfx. But there's a tautological map from fx to fx, namely the identity on fx. And under this isomorphism, by definition, that will be the corresponding eta. And then likewise, in the other direction, I need to tell you how to construct epsilon. I let x equal gy, and then I use the isomorphisms that I'm given that will give an isomorphism from the Hom set from gy to gy to the Hom set from fgy to y. And under that isomorphism, the identity on gy will go to something, and that's the epsilon y. Okay, so you can check that these two processes are inverse to each other. This is straightforward. This is how the correspondence works. And so are there any questions about the statement of this lemma? I'm going to leave some easy details for verification, but I've told you exactly what the correspondence is. Are there any questions about the statement? No, okay. Let's see. Okay, and now I want to give one kind of application of this alternative way to talk about adjunctions in terms of isomorphisms of Hom sets. So in the examples, I told you what the adjoint pair was together with the unit and co-unit. But often in practice, you start with some functor and then you ask yourself, is there an adjoint on the left or the right for this given functor? And if so, what would it look like? Maybe you don't know in advance what it's going to be or whether or not it exists. So one, you would like to know, you would like to know that if it exists, it's unique. And we can see this. So we can see what it would have to be if it exists. So given a functor from C to D, if a right adjoint G exists, together with all this data of eta and epsilon, the claim is it's unique up to natural isomorphism. And similarly, if I have G and I'm looking for the left adjoint, if it exists, it's unique. So here's a sketch of a proof. So fix my functor F, and let's suppose that the adjoint exists. How would I compute it, or how would I define it, construct it? So I would in particular need to tell you what its value is on an object Y of D. So consider this functor, which it's going to be a presheaf from C up to set. We'll take an element of C, an object, little x, it will apply F and then Hom into Y. Okay, so that's contravariant in X. And suppose that the adjoint functor G exists, then I would have these isomorphisms right here. And what would this be telling me? It would be telling me whatever this funny functor is, it would be the same as the functor which homs into some special object gy. And when we talked about Yoneda, we said exactly such functors were what is called representable objects, representable presheaves. And by the Yoneda lemma, if those exist, they're unique up to isomorphism. So if this object gy, which is the value of the adjoint functor, if it exists, it's unique up to isomorphism. It has to be what it is. And then similarly, using the way Yoneda behaves on morphisms, you can figure out what the adjoint must do on morphisms if it exists. And once you have that, then using the previous lemma, I can actually construct or figure out what the unit and co-unit are. So there is, in general, I should mention, there is a criterion for existence of adjoints. This lemma just tells you if they exist, they're unique, but it doesn't tell you when they exist. There's a criterion for existence of adjoints. It's not even that hard, but it would probably take at least another lecture. So I'm not going to do it, but you should know about it. It's called the Adjoint Functor theorem. And what it says is that under some additional hypotheses, certain necessary conditions for the existence of an adjoint are sufficient. So you can look this up if you want. What we're going to talk about now is at least what are those necessary conditions. So here are kind of the nicest property of adjunctions. This is about adjunctions and limits and colimits. So we'll say a little bit about this, and then we'll stop for the day before the seminar. Okay, so the situation is the following. So suppose I have a small diagram. I'm dealing with lots of functors, and my F was typically my name for a left adjoint. So I'm going to call my diagram something else. I'm not going to call it F today. I'm going to call it little delta. Suppose I have a small diagram delta from some index category I into a category C. And F is some other functor from C to D. Then I have the composite diagram. The composite diagram. And suppose, so actually, I don't want to imply that this is a left adjoint. I've been calling my left adjoints F, so let me just call this Phi. So suppose I'm fixing this data. And now suppose that the limit of the diagram delta and the composite diagram both exist. Then I would like to compare limit of delta and then apply phi to that to the limit of phi delta. And remember what a limit was by definition. It was an object that you know how to map into. So then, because I know how to map into limits, there's a natural map of the following form. So I could take the limit over the composite diagram. That's an object of D. It has a universal property. I know how to map into it. I claim that there's a natural map using that universal property from what I get by evaluating phi on the limit over delta, which is an object of C. So where does this come from? To give such a map, we just need to give its components, right? We need to give a, is it a cone or a cocone? So we need to give components So here, by definition of the limit, there are a bunch of projection maps, one for each object of I. So I have to give you these components and check the corresponding diagrams commute. The diagrams coming from the morphisms in I. So these components, so let me call this is what? This is maybe pi of phi delta I. So what is this component? I look at the limit over delta. That has its own projections, the p delta i's. And so I can apply phi to those. And since phi is a functor, everything will commute as necessary. So everything commutes with morphisms in I. So there's always this natural map from phi of the limit to the limit of phi delta. And I could do something similar with colimits. So likewise, if colimit of delta and phi delta exist, then in basically the same way, but using the kind of co-components, there's a natural map. And now the universal property of colimit is you know how to map out of it. It's the what? Initial cocone, I think. I always forget which one's cone and cocone by convention. But anyway, it's always the thing you map out of. So there's a natural map from colon over I of phi delta to phi of colon delta. Whose co-components, if you like, are what? So I have to tell you, how to write down these composites. So I have these co-components. Of the colimit. So let me write that. That's an iota. It's kind of an inclusion. Let me say it on J so it doesn't look so confusing. So by the definition of a colimit over phi delta, it receives all of these maps. It's the cocone, the initial one. And then I need to tell you what the restriction of this map is to those. What is it? Well, by the definition of the colimit of delta, it has its own co-components. So this is J for delta. And I just apply phi to that. Okay. And we say that phi preserves the limit of delta if, or the colimit, if the corresponding map is an isomorphism, the corresponding comparison map that we've just constructed. Is an isomorphism. So I'm going to give a statement about what this has to do with adjoint functors. We'll check this in the seminar. I'll state it as a proposition. It's not hard, but it's very important. So I'll state it as a proposition. This is the most important fact about adjoint functors. So suppose I have an adjunction back and forth between C and D. I'm leaving implicit the eta and epsilon. So suppose this is an adjunction. Then F, the left adjoint, preserves colimits whenever they exist on both sides. Whenever that makes sense. So the diagram has to have a colimit, and the composite diagram also has to have a colimit in order for there to be a comparison. And G preserves limits whenever that makes sense. So we'll check this in the seminar. I want to end today by giving an example, a kind of non-example. Where it's obvious that some limit or colimit is not preserved. So let's assume, yikes. Let's assume this proposition, which we're going to check in the seminar. This is example and non-example. So consider the adjunction, the free and forgetful adjunction for groups and sets. This looks like a set. I can make it into a free group. Or I could take a group and forget that it's a group and just remember it's a set. So then in particular, so F is a left adjoint, it should preserve colimits. In particular, it should preserve coproducts. Actually, everything I was going to say is true, but because what Dimitri did in the seminar last week was a little bit different from what I did, this example won't necessarily make as much sense to everybody. So let me, for simplicity, put abelian groups. So in particular, this is my free abelian group functor. So in particular, F, or the free abelian group functor, this preserves coproducts. What is the coproduct of abelian groups? It's just the direct sum. What is the coproduct of sets? It's just the disjoint union. So we're saying that if I take the free abelian group on the disjoint union of two sets, then that is the direct sum of the free abelian group on X plus the free abelian group on Y. Okay, and you could check that by hand. You're just saying if you form a linear combinations in a disjoint union of X and Y, you're just taking a basis for a free abelian group indexed by this disjoint union. You could break it up into two pieces, the part of the basis indexed by elements of X and the part of the basis indexed by elements of Y, and that would split the group as a direct sum. G, the forgetful functor would preserve limits. Also, the forgetful functor which is the right adjoint, will preserve limits in particular products. So if I had two abelian groups and I formed their product, the underlying set is just the product of sets. And that's something you know from algebra. If you want to form the direct product of two groups, in particular abelian groups, you take the underlying product of sets and then you define a multiplication on it. Or in this case, an addition because it's abelian. So the group, the product of abelian groups has underlying product set. However, the forgetful functor does not preserve all colimits. Can anyone think of a colimit? So it preserves limits, but not colimits. Can anyone think of a colimit that it does not preserve? So an example where there's a colimit of abelian groups, which is not the same as the colimit of the underlying sets. So we saw the coproduct of abelian groups was the direct sum. And the coproduct of sets was the disjoint union. But the direct sum of abelian groups is not isomorphic to the disjoint union of the two sets. Because on the left-hand side, A and B intersect at the 0 element. And on the right-hand side, it's a disjoint union of sets. They don't intersect. So these are not the same. And it turns out that these forgetful functors, although they don't preserve all colimits, they preserve certain special colimits called filtered. So that will be another exercise in the seminar. But one thing you can conclude from this is that whatever this forgetful functor is, it doesn't have a further right adjoint. Because if it did, it would be a left adjoint and it would preserve colimits, but it doesn't. And similarly, this free functor on the left, it doesn't preserve all limits. For instance, it doesn't preserve products. Therefore, it can't have a further left adjoint. Okay, so let us stop there for the day. And then we'll do the seminar. I have to look at the exact time it starts. I don't remember.